To get started on translations of the graphs of sine and cosine, I think we should just review the general graphs of sine and cosine first. So let's first of all look at sine of x, so y equals sine of x. The general graph, and I'm going to sketch two periods here just so we can kind of get a nice overview look at this. Is knowledge of the unit circle is important because then I can pick off these nice little quarter points. But the sine graph, the maximum value of a non-translated sine graph is 1, and the minimum value is going to be a -1. And then I also know that at the quadrantial angles, like 0 degrees would be here at the origin, then I'd have pi over 2, pi, 3 pi over 2, and 2 pi. There's some significant things happening. Sorry, this one's pi. And then I have the same things happening in the other direction for another period. And remember, this same curve will go on indefinitely using that same pattern, that same period. But we're just going to sketch two full periods here. Okay, so using those quadrantial angles, the sine of 0 is 0. So the sine curve, if it's not being translated, always starts at the origin. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is -1, and the sine of 2 pi is 0. Now this is going to move in the negative direction as well. The sine of negative pi over 2 is -1. The sine of negative pi is 0. The sine of -3 pi over 2 is 1. And the sine of -2 pi is 0. So this is going to be that smooth curve. Hopefully I can hit all these points. And it's not a sharp V shape, but that's the general shape of the sine curve. So the way I always think about that sine curve is it's starting at the origin. Let's go ahead and look at the cosine curve to review as well, and then we'll start looking at some transformations. We'll look at some of the ones that we've already done and some new ones as well. So when we start talking about the cosine curve, I still have that same maximum and minimum point, so I still have a 1 and a -1. So I have my quadrantial points at pi over 2, pi, 3 pi over 2, and 2 pi. And then moving in the negative direction, I'll have -pi over 2, -pi, -3 pi over 2, and -2 pi. Now the sine curve started at the origin, but the cosine curve starts up 1 unit. And these are non-translated sine and cosine curves. So if we talk about the cosine of 0, that's up here at 1. The cosine of pi over 2 is 0. The cosine of pi is -1. Cosine 3 pi over 2 is 0. And the cosine of 2 pi puts us right back at 1. Now over here in the negative direction, the cosine of -pi over 2 is going to be 0. The cosine of -pi is -1. -3 pi over 2 is 0. And -2 pi is back up here at 1. And again, this is a smooth curve as well. It's not a sharp V, so make sure when you sketch these on your exams, they're smooth curves. If you sketch them as sharp V's, that's incorrect. And so that is a two full periods of the cosine curve. And again, this quick that I keep in mind is always like this bird shape, this wing shape, and it starts up at 1 from the origin. So that's the sine and the cosine curves. Now the transformations that we've already learned already, let's go ahead and summarize those in a table with some new transformations that we'll be looking at as well. So when we start our table of translations and transformations, let's go ahead and look at the ones we've already reviewed from the last section. So first of all, we could use these for either sine or cosine, and I'm going to just focus on sine, but the same things will work for cosine as well. So table of transformations. So when you look at a graph and it's in a particular form, it's easy to look at it and see exactly what's going on with the transformations. Now the general form, like I said, we're going to be looking at sine, but you could also look at the same thing for cosines. So this could be an example of a general form of a graph. So the values for C, A, B, and D are going to be important here. So given these values, let's go ahead and break these down into smaller pieces. What does the y equal a sine of x mean? Well, that means the C I don't have, the B and the D are not here either, so I'm just focusing on this A right here. Well, what that is a vertical stretch or shrink. So vertical is top to bottom. By a factor of A. So that means if this A was a 2, the graph would be twice as tall. If this gray A was a 1/3, the graph would be 1/3 as tall. So it's a vertical stretch or shrink by a factor of A. This is also the amplitude. Now sometimes A could be negative, this could be a minus A. So if I take its absolute value, that's the amplitude. Now if A was negative, that would mean I would have a reflection, but we'll talk about that a little bit further down. What if we had something like y equal sine of bx? So in this case we don't have a c, a is an implied 1 here, and we do have the b, but there's no minus d. Well, what this is, it's a horizontal stretch by a factor of 1 over a. Now we also could have this value for b as a fraction. So what if this is 1 over bx? This would be a horizontal stretch by a factor of b. I need to fix this one up here. This is compression. It does the opposite, so horizontal compression. And I'm using b as my coefficient, so this should be 1 over b instead of that a. So it does the opposite. We think if you multiplied by b, it would stretch it out, but it's actually a compression by a factor of 1 over b. And if I have a fraction here of 1 over b, it's actually a stretch by a factor of whatever the denominator is, or the reciprocal of the coefficient that is in front of the x. Let's look at another one. Let's look at y equal negative sine of x. So there's an implied amplitude here of a negative 1 sine of x. So the standard amplitude of a sine or cosine curve is 1, so that's why we don't have the 1 written in, because it's an implied 1. But this negative is basically a reflection across the x-axis. So this is a flip. It's a reflection across the x-axis. It's a vertical flip. So if I have a point above the x-axis, it flips below. If I have a point below the x-axis, it flips above. And if I have a point right on the x-axis, it stays there. So these should be familiar from our last graphs that we looked at from a previous section. The newer ones that we are going to look at are horizontal translations, and then also a vertical stretch or compression, or horizontal stretch or compression. So the first one, let's go ahead and look at sine. Again, we're just going to keep using sine, but these would apply to cosine as well. Y equals sine x minus d. Now notice up above, when we had this b and 1 over b, those are inside the argument of the sine function. Now this minus d is inside the argument of the sine function as well. And anytime you're working within the argument of the sine function or the cosine function, what ends up happening is it's horizontal, whether stretch, compression, or translation. Now a couple things I want you to know about. Let's say we had something like y equals sine of x minus pi over 2. This does not equal the sine of x minus pi over 2. You have to be really clear about that. So always put parentheses around the arguments of your trig functions in order to clarify what you're doing. And I'll especially be looking for this during your exams when you're showing your work on things. So if we had y equal the sine of the quantity x minus d, this would be a horizontal translation to the right d units. So again, it's within the argument of the sine function, so it's horizontal. Also notice it's the opposite. If it's a minus d, I move to the right. Now let's look at another one. What if I had a plus d? This would also be a horizontal translation. This one would be to the left, d units. Now notice it's opposite. This is a x plus d, but I moved to the left. So anytime it's within the argument, it's horizontal, and also it's always opposite of what you would think. So if we come up here, this was within the argument up here, and if you'll notice that it's the opposite. You'd think it would be a horizontal stretch, but it's a compression by a factor of 1 over b. So those are some things to look out for. Now these ones that we just looked at are also called phase shift. So this is also known as phase shift. So let's say I moved to the right pi over 2 units. My phase shift would be pi over 2. So you'll see the terminology phase shift, and that's what it applies to. So now we can also look at, I think our very last one would be a vertical translation. And we always do this last when we're graphing. So if we had something like y equals sine of x and then plus d. Now keep in mind, we'll make it plus c just to use a different variable. Keep in mind that this is not equal to the sine of x plus c. These are two different things. So you always have to have parentheses around the argument of your trig function so you know exactly what you're talking about. Well, what this is a vertical translation. So it's basically pick your graph up and move it, c units. Now if this was c units that were positive, I would move it up, and if it was c units that were negative, like a negative c, I would move it down. Now you'll also see this written y, I'll write it down here, y equal c plus sine of x, just to make sure that sometimes we don't make a mistake like this. So always put parentheses around the arguments of your trig function. I'll always be looking for that. So if we go back up to what we had at the top, and again we're writing this for sine, but we could use it for cosine as well. Let's go ahead and kind of break down what each of these pieces ends up meaning. So c would be our vertical translation. Okay, and then this value of a, I'll move it down here. A is a vertical, and notice these are both on the outside of the trig function. Stretch or shrink, depending on whether if it's a whole number or a fraction. It's also known as the amplitude. And then this value of b that we have right here, b is going to be the horizontal stretch or compression, and it's inside the argument of the trig function, so that's why we have horizontal. Remember, it's always opposite of what you would think it would be. And then this minus d, we'll make that one orange so we can see the difference. D is the phase shift. This is basically, with the phase shift, this was a horizontal translation. It's inside the trig function, so it's horizontal, and also it's opposite of what we think because it's inside the trig function. Well, now that we have all this information down, let's go ahead and come up with a way or a method that we can use to consistently graph a trig function. And in your textbook, if you read the online text or the e-text, this is called method 1. And there's several different methods and many different ways that we can do this, but we're just going to follow through with this method 1. Now this method for graphing trig transformations, if you follow through step by step, it will work really nice every time. So the first thing we do is we find an interval, and basically this is going to be the period. Find an interval whose length is 1 period. Now remember, for the period we could take 2 pi and we could divide it by this coefficient of b that we have up here in this. So this value, this purple b, we would take our period of 2 pi for sine and cosine and we would divide it by b. So if we come up here where we have this horizontal stretch or compression, I guess we could include that information as well right here. The new period will be 2 pi over b. And this would be true for sine and cosine. Now this one, the new period, will be 2 pi over 1 over b, but when you divide by a fraction, you multiply by the reciprocal, this ends up being 2 pi b. Okay, so that has to do with what the new period will be. So that's what we're talking about down here. So when we say find an interval whose length is 1 period, and that period is based on the 2 pi over b, we do this by solving. We take the argument of that trig function and we put it into an inequality, and notice each end of the inequality is basically where a typical period for sine would start and end. So a period for sine is 0 to 2 pi, and what I'm doing is I'm taking this argument right here and I'm now going to solve for x to figure out where my new endpoints are and my new start and end points are, I should say. Now when we solve that for x, the next thing we want to do is we want to divide this interval up from step 1. This first step above, into 4 equal parts. And when we do this, we will obtain 5 key values. And basically these 5 key values will be maximum, minimum, and cross points where it would cross. Next, we'll take these 5 key values and evaluate the function. Now what this is going to give me are maximum points, minimum points, and basically your cross points or your middle values. Okay, and the last thing that we're going to do, we're going to plot the points. From step 3 and join them with a smooth curve. And remember, smooth is the key word here, because they're not sharp like a W like this. They're a smooth curve. So make sure you make that distinction. Now I think one of the best things to do is to just look at a lot of different types of problems here, and I'll be pulling in some graphs from my math lab, so they'll be a little bit familiar to you, and we can compare them to what your homework will look like. But one thing I want you to keep in mind is you should be able to look at these graphs, and when you look at them, be able to decide how many transformations are here, and not only how many transformations, but which transformations they are. So you should be able to, at a quick glance, decide that about a graph. Okay, it's coming in kind of small, but here we have y equals sine of x plus pi. Well, if we come and look at our list here, this looks just like this, sine of x plus d. So this is a horizontal translation to the left, d units. So this would be a horizontal translation to the left, but not d units, because we know our value for d is pi, so it'd be pi units. Now let's think about this. The sine curve typically starts at the origin and looks like this. So what I'm doing is I'm taking this point and I'm moving it over pi units. So I'm taking this point and I'm moving it pi units. I'm taking this point and I'm moving it pi units. Well, it used to be pi over 2. So if I move it to 0 and then to here, this point I'm going to move pi units, and you're going to get to see the little bit of a pattern develop here. this point would move pi units, and then this point would move pi units as well. So this would end up looking like it's still going to move up, come down, and cross. So it's definitely not moving to the right, and this graph is moving to the right, so it can't be that. This graph didn't move at all, it's just our sine curve, or really close to it, so it can't be that one. This one is moving pi units to the left. This one is moving pi units to the left, but notice this one moves down. And because it moves down, that's not the correct shape for the sine curve. So our correct answer here is the graph of D. So you should be able to just glance at a basic graph like this and be able to graph it based on that. Now let's go ahead and look at our method for graphing. So for our method for graphing, what we do is we take step 1, we take this x plus pi, and we bracket it in between the period for sine, which is 0 to 2 pi, and then I solve for x. So I subtract pi, and I subtract pi from the middle and both sides, and I end up with negative pi less than or equal to x less than or equal to 2 pi minus pi is pi. So this is saying my new start point and my new end point will be given. So this is my end point. Okay, so that would be the start and the end. Now step 2, and again I'm just coming up and reading off these, it says divide this interval from step 1 into 4 equal parts. Okay. So step 2, divide the interval negative pi less than or equal to x less than or equal to pi into 4 equal parts. Okay, so I think the easiest way to do that is we would see the distance from negative pi to pi is 2 pi units. And so that gives me my total width of a period. Now there's several different ways that we can do this, but let's go ahead and look at one approach. We could do pi minus a negative pi to get that width we were just talking about. Okay, and so that would be pi plus pi is 2 pi. And then we could say we want to take this and we want to divide it into quarters. So we divide it by 4, and I would get pi over 2. So this would be the value or the width of each of those intervals. So that I would add this to the start point. So my start point was negative pi, and then my next point would be negative pi plus pi over 2. And negative pi plus pi over 2 is a negative pi over 2. My next point would be negative pi over 2 plus another pi over 2 is 0. My next point would be 0 plus pi over 2, which is pi over 2. And then my last one would be this pi over 2 plus pi over 2 is 2 pi over 2, or pi. So those would be my 5 important numbers. So they were negative pi from here, negative pi over 2, 0, pi over 2, and pi. So these are my 5 important values, and I have 1, 2, 3, 4 intervals, and each of those intervals has a width of pi over 2. So that's what these points are up here. Here's my negative pi over 2, 0, positive pi over 2, and pi. So that's where these values came from up here. Okay, so now I should be able to plot points with these. And you'll already see the advantage of being able to recognize your graph and just go ahead and see, oh, it's a horizontal translation to the left so many units. It's a lot shorter than these graphing methods. However, these graphing methods are really handy for more complex problems. So my next one was to evaluate the function at these points. So I'm going to have some x values. That I'm going to plug in, and when I plug in the x values, I'm plugging in these 5 important numbers. So it'd be negative pi over 2, 0, pi over 2, and pi. These are our nice quarter points. So those are, if I just had a standard sine curve, is what I would be plugging in, are these x values. But we don't have that. We have x plus pi. So if we take x plus pi, this would mean I'd have negative pi plus pi is 0. negative pi over 2 plus pi would be a positive pi over 2. 0 plus pi is pi. Pi over 2 plus pi is 3 pi over 2, and pi plus pi is 2 pi. Okay, so I'm taking each of these values of x and I'm plugging them in down here. And this chart that I'm creating then will allow me to evaluate this. So now what I want is I want to plug sine of x plus pi. So now I already know what x plus pi is 0, so I can just go ahead and plug that in here. The sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is negative 1, and the sine of 2 pi is 0. So these are the points then that I want to plot. I want to plot the ordered pair negative pi, 0. Negative pi over 2, 1. 0, 0. Pi over 2, negative 1. Pi, 0. This row in between are just, it's basically a row to help you calculate some values. So again, the points I want to plot are negative pi, 0. Negative pi over 2, 1. 0, 0. Pi over 2, negative 1. And pi, 0. Now my final step was to plot those points and connect with the smooth curve. So that'll be step 4. So this is the graph of y equals sine of x minus pi, or x plus pi, I believe it was. I better go look. Yep, x plus pi. So clearly we need to make sure that we have enough room on either side of my vertical axis. My maximum value was a 1, my minimum value was a negative 1, and then these quarter points I need would be negative pi over 2, so I'm going to call this a negative pi over 2, 0 is right here, pi over 2, and pi. And it's important that we plot these points and we mark them as well. And I could do more than one period, so if I wanted to I could keep moving these directions. So here's the point negative pi, 0. Here's negative pi over 2, negative 1. No, wait. Negative pi over 2, positive 1. Whoops. I don't know what's popping up here. 0, 0. Pi over 2, negative 1. And then, of course, we have pi here. And so pi was 0 again. Okay, so that's the sine curve. It's just moved over pi units to the left. And so that would be my graph. And again, if you can recognize what this is right away as this translation up here, you don't have to go through all these methods for graphing. Now for more complicated problems, you definitely will. So let's go ahead and look at a few more. And these next ones, I just want to take a quick glance at them and see if we can determine what's going on with each one. I'm not going to go through all the method steps, only for the more complicated ones. So this would be cosine x plus pi. So we already know what this one's going to do. This is going to be a horizontal translation. Now this is also called a horizontal shift because I'm picking up the graph and moving it to the left, because it's always opposite, pi units. So you should get used to that terminology. Translation and shift mean the same thing. Well, let's go ahead and look at a quick graph. We know our cosine graph starts at 1, goes to negative 1. Now I'm going to go ahead and split this up a little bit. Our nice quarter points, pi over 2, pi, 3 pi over 2, 2 pi. Now if I kept going, 3 pi over 2, 4 pi over 2, this would be 5 pi over 2. This would be 6 pi over 2, or 3 pi, and then 7 pi over 2. And again, I don't need these many points, but if I want to extend this in the other direction, I want to make sure that I have plenty of points to plot. I'll go a little bit further in this direction as well. Negative 5 pi over 2, and a negative 3 pi. Okay, so the first thing I'm going to do is I'm going to graph my standard cosine curve. So the cosine of 0 is 1, the cosine of pi over 2 is 0, the cosine of pi is negative 1, cosine of 3 pi over 2 is 0, and the cosine of 2 pi is 1. So I kind of get this bird wing shape. And this is going to go on forever following this same pattern. So this is the cosine curve. And I have to be careful here. Yeah, it's hitting those points pretty close. Okay, so this is the cosine curve. So y equals cosine of x is in orange. Now what's happening here then with the cosine x plus pi all in parentheses, I'm moving my graph to the left pi units. Okay, so what this means is this point right here is moving over here pi units. This point right here at pi over 2 will move left pi units. This point right here at pi will move to the left. This point at 3 pi over 2 will move to the left pi units. This point at 2 pi will move to the left pi units. And the same pattern will continue. So again, I still have that same bird wing shape, but it's just moved over. Now let's go ahead and keep looking at this graph. So I start up at 1, and then I move down and back up at 1. So I'm up at 1, and I move down, and then back up, move down again. So if you notice at every multiple of pi, I'm either up at my maximum or down at my minimum. So at negative pi, pi, and 3 pi I'm maximized, and at I guess I could come over here and finish this one as well. So at negative 2 pi, I'm at my minimum, 0, and up here at 2 pi again. Now this is a smooth curve, and so my blue line is the actual graph, and you can just see that the orange line, if I just pick it up and move it to the left pi units, they would be identical. So y equal cosine x is in the blue. So again, it's a lot easier if I can recognize these and then just graph them based on the transformations. Let's go ahead and find another one. I want one we'll have a couple transformations on. Okay, let's try this one. So use transformations to graph the following. Now this one we should be able to identify the transformations. We might have to use the method if there's too much going on here, the 4-step method. But this one should actually be pretty simple. So this one is our standard sine curve. And then this -2, this is going to be a vertical translation or shift, I mean it's the same thing, down 2 units. It's on the outside of the trig function, so it's going to be vertical, and it's a -2, so it means it goes down 2 units. So what I'm looking for is a sine graph basically that moves down 2 units. So the best way to start would be to think about what the sine curves look like and then move it down 2 units. Now this one I'm going to make sure I leave enough room underneath to be able to move it down 2 units. So here would be 1, here would be -1, here would be a -2. Okay, now our points, there's nothing going on horizontally, so the pi over 2, pi, 3 pi over 2, and 2 pi shouldn't be making a huge difference here. These should not be moving basically because there's no horizontal movement at all. So let's go ahead and graph just y equal sine of x. So that would be 0, pi over 2 is 1, 0, 3 pi over 2, 2 pi. And let's keep moving in this direction as well. And this is just kind of my parent graph that this is going to be built on. So it's just going to be dotted. Now what I'm going to do is I'm going to take this whole graph, I'm going to move it down. Again, it's down 2 units. So this point that's at 0 moved down 2 units. And I've already run out of room. So I'm going to call this one negative. I'm going to rescale this a little bit. Otherwise I'm going to run out of room. So I'm going to call this down here as -1, -2, and -3. Okay, so this point moved from 0 down 2. So each of these points that are at 0 will move down 2. So maybe I can pull them all down. Now this point right here at 1, if I move it down 2, will move down to -1. And then this point that's already at -1 will move down to -3. And again, the scale is a little bit off, so it's going to look a little squished. Here's the other one. Move down to -3. So now this is my actual graph, and I connect them with a smooth curve. So that's my new graph. Now notice this line right in between here still is that line of symmetry. It still cuts it in half just like the x-axis. So basically I just picked up this whole orange dotted graph and I moved it down 2 units to get the red graph. And again, you could go through the 4 steps method to find these values as well, but sometimes it's a little easy if we can just identify them real quick and we get used to using those transformations. However, sometimes they're more complicated and the 4-step method will be really handy. So this next problem that you might run across in my math lab, it doesn't ask for a graph, it asks for specific values, and so I think it's important to be able to use that 4-step method to come up with these. Okay, so first of all, let's go ahead and write this off to the side. We have a cosine curve, 3 cosine 7x minus 2. Now the way that we want this to look is y equal, now I'll show you where I'm getting this from. This is from our work clear up here. This is like our standard form right here. This is the c plus a sine. I guess I could just copy it. Y equals c plus a sine. And again, that's kind of our standard form. That's what we want to be able to match. Now if you notice in this case, I don't have a c. So I don't have a c. I do have an a, so I have a is 3. This b looks like it's 7, but this doesn't look like 7 parenthesis x minus d, so I need to do a little work here. So this is going to be 3 cosine. I'm going to put up my bracket, and I'm going to factor out a 7 here. And I want a minus sign as well. So if I factor out a 7, you might say, well wait, there's no 7 there to factor out. Well basically what I can do is I can take this 2 and I can write this as 7 times 2 over 7. Now I can factor out a 7 and I'd be left with minus 2 over 7. Now if I took this and redistributed the 7s would cancel and I'd be left with x minus 2. So what I have here then is the amplitude. So this is the amplitude. And it's always the absolute value. So this is 3. So right away amplitude is not 2, so I can throw that out. So it's got to be B, C, or D. Now the period, I take the old period for cosine, which is 2 pi, and I divide it by this value right here, b. So it should be 2 pi over 7. So not 7 pi over 2, 2 pi over 7. So it's got to be C or D. Now the last thing I look at then is phase shift. Now phase shift is the amount that this graph is moving to the right or to the left. Now if you do not factor out this 7, if you just leave it in this form right here, you'd say, oh, the phase shift is 2. It's whatever comes after the variable. But that's not accurate. I have to rewrite this with the 7 factored out, and so my phase shift is actually that value for 2 7s. So you have to be really careful about how you write this out. you have to write it in factored form. Now, real quick, let's go ahead and go through that one more time. That 7x minus 2, if I want to factor out a 7, I want to know what will go here, what goes with the question mark. Well, it's not a 2, because again, I factored out a 7, and you might say, well, there's no 7 there to factor from away from the 2. Well, what I can do is I can put a 7 in. I can multiply the top by 7. If I divide the bottom by 7, it keeps that balance. So when I do that, and I factor out this 7, I'm left with 2 over 7, and that's my phase shift. And this is a trick you're going to want to know how to do, because it comes up an awful lot. Okay, let's go ahead and find a little bit more complicated one where we can use the 4-step method. And again, it's going to be important that you be able to glance at a problem and see how many transformations there are, and also to be able to glance at a problem and figure out exactly what your approach is going to be to graphing it. Okay, so that one looks a little too easy. Let's do this one. Looks more complicated. Now this one is actually in my math lab, and it asks us to graph it. So before we actually graph it, I want to make sure that we can go through this step by step and find all the values and everything that we're going to need. So let me pop this problem in, and then I'll also show you how to graph these in my math lab, because there's a little bit of a trick to it. So this one is asking you to graph it in my math lab. So in order to graph it in my math lab, you have to know what the general shape of the graph is, and then you also need to know the period, the amplitude, the phase shift, etc. Okay, so I would like to put this in the form y equal c plus, I'm using the same one up here, a, but I'm not going to use sine here, I'll use cosine of b times the quantity x minus d. Well, right here on this problem, I don't have a plus c, I don't have anything on the outside, so I can get rid of that. And then this will be y equal a is 1/2 cosine bracket. Now this is the coefficient in front of the x is a half, so I have to factor a half out. Now the question is, what goes here if I factor a half out? Well, this is a little bit of a tricky part. You might say, well, there's not a half there. Well, there is a half there. We can do this one of two ways. You could realize that 6 is actually 2 times 3. And you can say, oh, there's a 2 that I could pull out in each denominator, so that's a half. And if I factor out in a half, I'd be left with pi over 3. Now, if you didn't notice that, you could rewrite this, and you could say, okay, this would be a half x minus pi over 3. And you could say, well, I wanted 2 to pull out, so I'd multiply the top and bottom by 2. And if I do this method, I'd be left with, pulling a 2 out, I'd be left with that 2 pi over 3. But that's not the correct phase shift. So actually, I'm sorry, I did that incorrect. This would be pi over 6. I copied the problem wrong. So this would be a 6 here. And then when I reduce the 2 pi over 6, I'm left with pi over 3. So I can get the same thing either way, whether you recognize there's a factor of 1/2 already in the denominator, or if you create one, this would be pi over 3. So here, my amplitude is equal to 1/2. The new period would be 2 pi over 1/2, which is the same as 2 pi over 1 times 2 over 1. So my new period is 4 pi, so this is going to be really stretched out. And my phase shift is going to be pi over 3. And this again is going to be to the left. Okay, so this is the same problem that we have in my math lab. And when you graph these in my math lab, the first thing you need to do is you need to choose the sine or the cosine curve. So this tool is the sine curve because it starts at the origin and it has the sine shape. This has the bird shape for cosine. So I click in and click on the graph, and here's all the amplitude period, this pop-up box. So I change the amplitude to a half, just like I have here. The period should be 4 pi, and that's 12.57. And if you're not sure about that, you can grab a calculator. I'm going to double check it. 4 times pi, 12.57, yep. Vertical shift is 0 because there's no plus c anywhere, but the phase shift was pi over 3. Okay, so let's go ahead and put in that phase shift of pi over 3. Now my computer's in tablet mode, so I can't type on my keyboard. So let's see if I can get a keyboard to pop up over here so we can put in pi over 3. Okay. So amplitude was 1/2, period was 4 pi, and our phase shift, and again I'm trying to get this to pop up, here we are, pi over 3, and I don't have a pi, so I'm going to type in pi divided by 3, and again this is just because my computer is in tablet mode. And then when you click off of that, it will create your new graph for you, and you can save it and then check it from there. Okay, so that's how you'd graph one of these in my math lab. I'm going to copy and paste this into our problem so we can see what the graph looks like. Whoops, and the graph disappeared. I wonder what happened to it. Must be the new problem. So anyway, I'll go back and paste it in later if it will let me grab it again. There it is. And you can see the maximum and minimum points. You can see the amplitude change to 0.5 up here. So using that tool in my math lab is pretty handy. But knowing how to use that 4-point method is important as well. There it is. Okay, let's do one last problem, a little bit more complicated problem. And this one will have that 4-step method. So for this one, we're going to use a problem from my math lab, but we're not going to be necessarily graphing it in my math lab. We're going to be using that 4-step method. So again, we can look at this and we can see, okay, there's a -1, so that's a vertical shift. The vertical shift we always do last. 4 is the amplitude change. X plus pi over 6, that's going to be a phase shift. We don't have a horizontal stretch or compression. So if I write my general form here, again, that's C plus A. This is sine. And here we have that b times the quantity x minus d. So that's our general form. So we match this, and I'd have a -1 plus a sine. Now my value for b here is just an implied 1, if we want to think about it like that, x minus a negative pi over 6, because we need that minus sign right here. So this value of b is 1 isn't really all that important. I'm going to just put it in just so we can see it here. So this would be a vertical shift down 1 unit. And I'm going to do this last. We always have to do the vertical shifts last. The 4, the a equal 4, is the amplitude. So I look at the absolute value. This would be a vertical stretch by a factor of 4. Okay, now the b doesn't come into play here really, but I want to show you what it means. B is 1. What I would do is I'd take the old period and I would divide it by b, so there's no change there. So the period stays the same. And then lastly, I'll have this value for d is negative pi over 6. Now it's negative pi over 6 because this value right here was negative, minus a negative. So this is my phase shift. This means I'm going to move my entire graph I'm going to move the entire graph to the left pi over 6 units. So remember here it was a plus pi over 6, but it's always opposite. So the opposite of plus pi over 6 would be a negative pi over 6. So we have a lot of information here. It would be really hard to graph this just if we started trying to plot some points. So we're going to use the 4-step method. And then we'll graph it from there. So the 4-step method, step 1. Step 1, if I remember correctly, let's go ahead and go all the way back up to the top here. Find an interval whose length is 1 period by solving for 0 to 2 pi. So we can certainly do that. And then once I find that, I'm going to divide it into those 5 key points, evaluate the function, and then connect the points, plot the points, and then connect the points with a smooth curve. So step 1, I'm going to take my argument, this x plus pi over 6, and I'm going to find the start and end points for my new graph for this transformation here. So the way I would do that then is I'd subtract pi over 6, and I'd end up with negative pi over 6. These cancel, so I'm left with x, and then 2 pi minus pi over 6. Well, I need a common denominator here, so that would be 12 pi over 6 minus pi over 6 would be 11 pi over 6. So this is my endpoint for 1 period. I can always do more. And this is my start point for 1 period. Okay, so that's step 1. Step 2, I want to split this up into 4 equal intervals. And with these 4 equal intervals, that would mean our 5 special points is what they call them. And these would be my max, my min, and my midpoints. So one way that we could do this, and again there's many different ways that we could do this, but I could look at 11 pi over 6, I could figure out the width of 1 period. So that would be 11 pi over 6 minus a negative pi over 6, which would be 12 pi over 6, which reduces to 2 pi. And this makes sense because remember up here, our period didn't change, it stayed 2 pi, so I would expect to see this, but my endpoints are changing. Then what I want to do when I split this up into 4 equal intervals, I want to take this 2 pi and I want to divide it into quarters. So when I reduce that, that's pi over 2. This would be the width of each quarter. Okay, so I'm going to start at negative pi over 6. That's my start. And I'm going to go to my next point. So this is my first point. Here's my second point. This would be a negative pi over 6 plus pi over 2 because that's the width from up here. So this would be a negative pi over 6 plus 3 pi over 6 would be 2 pi over 6, which is pi over 3. So that would be my second point. My third point would be this 2 pi over, I'll just use the pi over 3 I guess, but I'll show you the advantage here of keeping them in fractional form and not reducing the fractions. Pi over 3 plus pi over 2, I'd have to find a common denominator. That would be 2 pi over 6 plus 3 pi over 6 would be 5 pi over 6. Okay, my next point, trying to sneak these onto a page, would be 5 pi over 6 plus pi over 2, because again that's the width of my interval. 5 pi over 6 plus pi over 2 would be the same as 3 pi over 6. So this would mean 8 pi over 6, which is 4 pi over 3. Last point here, I know what my last point better be. We'll see if it turns out. Would be 4 pi over 3 plus pi over 2. Common denominator would have to be 6, so I'm going to multiply 8 pi over 6 plus 3 pi over 6 would be 11 pi over 6. And this should be my endpoint. And we can see from up here, that is my endpoint, so it turned out just right. So my important points here, my special numbers are negative pi over 6, pi over 3, 5 pi over 6, 4 pi over 6, and 11 pi over 6. Now, I always like to think about these in terms of a common denominator. So the common denominator between the pi over 6, pi over 3's would be the pi over 6 multiple. So what I'm going to do next is I'm going to create a table and I'm going to plug them in and evaluate. Now there's a lot going on here. So it's nice to create a table that allows us to kind of break this down step by step. So let's go ahead and remember what our function was. Y equal -1 plus 4 sine x plus pi over 6. Let me just double check that. -1 plus 4 sine x plus 5 over 6. Yep. Okay, so our table allows us to plug one thing in at a time and kind of keep track of values. So remember, my start point here was -pi over 6. My next point was pi over 3. And again, I want you to just keep in mind that this is the same as 2 pi over 6. My next point was 5 pi over 6. Has that common denominator of pi over 6. My next point is 4 pi over 3. And keep in mind again that this is really 8 pi over 6. And my last point here is 11 pi over 6. Now I'm not using that pi over 6 multiple information to plug in. I'm using them for graphing. So what we're going to do is we're going to plug this into the argument first, x plus pi over 6. So that would be my first step here. And then I'm going to take the sine of x plus pi over 6. And then I'm going to take 4 times the sine of x plus pi over 6. And then my final step would be to take -1 plus 4 sine of x plus pi over 6. But we're going to break this down step by step because these are some pretty big numbers. So we're going to break it down to make this a little bit easier to work with. Okay, so x plus pi over 6. So I'm taking -pi over 6 and I'm plugging it in here. -pi over 6 plus pi over 6 is 0. And again, the reason I'm using the 2 pi over 6 is it's easier to add to pi over 6. 2 pi over 6 plus pi over 6 is 3 pi over 6, which reduces to pi over 2. 5 pi over 6 plus pi over 6 is 6 pi over 6, or pi. 8 pi over 6 plus pi over 6 is 9 pi over 6, which is 3 pi over 2. 11 pi over 6 plus pi over 6 is 12 pi over 6, which is 2 pi. Now I want to take the sine of x plus pi over 6. So the sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is -1, and the sine of 2 pi is 0. Now I want to take 4 times that number. So 4 times 0 is 0. 4 times 1 is 1, or is 4. 4 times 0 is 0. 4 times -1 is -4, and 4 times 0 is 0. Now from all of that I want to subtract 1. 0 minus 1, 4 minus 1, 0 minus 1, -4 minus 1, whoops, -4 minus 1, and 0 minus 1. Now what I'm going to do then is to plot the points. Well, you might say, well, which points? We have a lot of points here. Well, they would be basically each of the x values from up here, and the y value, or the final output from down here. So our x and our y. So these are the points that we're going to plot. Now specifically, I want to plot the ones that are the multiples of pi over 6. I don't want to reduce those just because they're a little bit harder to work with then. Okay, so let's go ahead and graph this. Need a little bit smaller pen. And I need to go from -pi over 6 to 2 pi over 6 to 5 pi over 6, 8 pi over 6 to 11 pi over 6. So I'm looking at multiples of pi over 2. So if I really wanted to be clear here, I could look at this as -pi over 6. 0, this would be pi over 6. 2 pi over 6. 3 pi over 6. 4 pi over 6, etc., all the way up to 11 pi over 6, because that's my endpoint. And this will make sure I don't forget anything or lose anything, and then I can always reduce these a little bit later. So if I look at this at -pi over 6, this says I should be at -1. So here's 1, 2, 3, negative 1, negative 2, 3, negative 4, negative 5. So at negative pi over 6, I should be at negative 1. I'm going to have to move that a little bit. There we go. At 2 pi over 6, I should be up at 3. And at 5 pi over 6, which is right here, I should be down here at negative 1 again. It's going to crowd that a little bit. And at 8 pi over 6, I should be at negative 5. And at 11 pi over 6, I should be at negative 1. Okay, so let's look to see what we have as we connect these dots. Kind of hard to see here. And that's my sine curve. So remember, your basic sine curve looks like this, and that looks identical to that. It just looks like it's been scooted over and it's stretched and then shifted down a little bit. So that's the 4-step method. And if you look at the 4-step method, it allows me to find the maximum and minimum points. And it's not telling me where I cross the x-axis, but it's telling me about this line of symmetry here, or the center line where I split. This is a long video, but these are long problems, a lot of detail to them. You need to make sure that you can graph these points and graph the 4-step method, and as well as recognize transformations, because we'll be using this for tangent and cotangent and secant and cosecant next. As usual, if you have any questions, let me know, and good luck.